Right, so this video is going to run through Born-Haber cycles as per the Unit 5 specification, or part of the specification from the old AQA syllabus. It's within the thermodynamics topic, and it's quite a big section. You can almost guarantee something in an exam is going to come up relating to something in this video, whether it be a definition or whether it be an actual cycle itself. So Born-Haber cycles, so they tie back into the AS unit in that they are very heavily involved with Hess's law, so the kind of cycles that you may have come across there. So these cycles being ways of determining enthalpy changes within reactions, and they base themselves on this idea that Hess's law, and the way the application of Hess's law is that a reaction is the enthalpy change for the reaction is independent of the route that we take to get there. So it's easy to sort of see it as an example. So if we imagine A plus B gives us C plus D, and we have an enthalpy change for that reaction. Well, if we were to go via E and F, so we went from here to here, we would still find that the overall enthalpy change to do that would be equal to this. So it would be the same as that. And this is what Hess's law means. So basically, the definition then is the enthalpy change for a reaction. So the enthalpy change for a reaction is independent of the route taken. And this is quite good because it means actually we can use this this idea here, this definition of Hess's law, and we can ultimately apply it to various situations, and we can work out enthalpy changes that we might not be able to in experimentally, or might not be able to enthalpy changes we might not be able to measure directly. We can measure going through different intermediate routes, which is quite useful. And so the application A2 is these thermochemical cycles, these Born-Haber cycles. The same Haber guy actually that did the Haber process, as far as I'm aware. So, first thing within this topic is some definitions. Now, if you remember back to AS, you had a variety of definitions. Here you have quite a few, unfortunately, and there are a lot of definitions here that you need to know, and you've just got to get on and learn them. Really, there's no other way to look at it. So what I'll do is they'll obviously come up now, and then I'll run through each one, sort of briefly what they are, and obviously the reactions that are occurring in each one. So the first one then, enthalpy of formation. So an enthalpy of formation, as it says, is the enthalpy change when 1 mole of a substance is formed from its constituent elements in their standard state under standard conditions. This idea of standard there being in this case, standard conditions, obviously 100 kilopascals and 298 Kelvin, and standard states being whatever they are. So hydrogen being a gas, bromine being a liquid, magnesium being a solid. So that's our standard states. And the equation we've got here is Na, solid, state symbol of S for solid, plus half Cl2, state symbol of G for gas, goes to NaCl, solid. So you can see there the state symbols that I've got. And note that we're not balancing up with 2's on the right hand side and then a 2 for the Na. We're actually halving the Cl2. The reason being that by definition we are forming 1 mole of substance, therefore we can't have a 2 there. That would actually be incorrect to match the definition. Second, ionization enthalpy, or ionization energy is the other one. And the definition for that is the enthalpy change when 1 electron is removed from each atom in a mole of gaseous atoms to produce 1 mole of gaseous ions with a +1 charge. You can see various wordings there, but that's the wording that I tend to like. You can also see a mole of electrons is removed from a mole of atoms, blah blah. I prefer the 1 electron removed from each atom in a mole of gaseous atoms, but it's up to you. The way to write that then, you've got an option of Mg. You must have state symbols here. The electron doesn't need a state symbol, but the species that you start with and end with, they must have state symbols, both G's. So we've got magnesium, Mg, gas. We can either have minus electron, goes to Mg plus gas, or we could have Mg gas, goes to Mg plus gas plus electron. It's just algebra, you put it on either side. It's better to write on the other side, so it's a plus electron, but it's kind of really, it's a matter of preference. Third one then, enthalpy of atomization. I'm just going to give you the definition for an element, but the opposite is obviously, or the same applied to a compound is true. So the Enthalpy change when 1 mole of gaseous atoms is formed from the element in its standard state. Again, and here I've got the example of sodium, so NaS going to Nag. Nice easy one that. Fourth, the bond dissociation enthalpy. Enthalpy change when 1 mole of covalent bonds is broken into 2 gaseous atoms or free radicals. And what we're here is looking for the mean. Often we'll get the term mean bond dissociation enthalpy, and the fact that it's mean is it's averaged over a variety of compounds. That's really where we're looking at. An example there is Cl2 brackets, obviously G for gas, going to 2Cl G, or you could write that as the 2Cl dot as a per usual sort of free radical. Fifth, a new one now. Some of these other ones, obviously enthalpy of atomization was new, but this one now, electron affinity, another new one. The opposite of ionization energy. So electron affinity, it's the enthalpy change when each atom in 1 mole of gaseous atoms gains 1 electron to produce 1 mole of gaseous minus 1 ions. Now, it's worth pointing out for both this one here, this fifth one, the electron affinity, and also the second one, they are the first electron affinities and first ionization energies. You can obviously have second, third, and you've got to amend those definitions as such, but I've just given you the first one there. And the what we could have there is a Mg gas plus electron to Mg minus gas. Obviously it's gaining negative charge and therefore becoming a negative ion. Sixth one, lattice dissociation enthalpy or lattice formation. And you can get it given either way. Now bear in mind they are different wordings. Now this one, enthalpy change when 1 mole of ionic crystal is broken into its constituent gaseous ions. That is the dissociation enthalpy. That's dissociation enthalpy. Lattice formation would be the opposite. So sticking with the dissociation, NaCl being broken down as a solid, being broken down into gases, the sodium ion gas and the chloride ion gas with their respective charges. Seventh one, we've got enthalpy of hydration. So this is the enthalpy change when 1 mole of gaseous ions become aqueous ions. So that's Na plus here, gas plus Aq for aqueous, going to Na plus aqueous. So we're going from gaseous ion to aqueous ion. And finally, the enthalpy of solution. So this is a bit of a longer one. Enthalpy change when 1 mole of an ionic solid dissolves in a large enough amount of water to ensure that the dissolved ions are well separated and do not interact with one another. And this time, similarly involving the AQ, very similar to the one above in some ways, that we're forming, it's similar, but it's actually not the same at all, really, looking at it. NaCl then, solid, plus aqueous again, goes to Na plus aqueous and Cl minus aqueous. So, what we've got there are obviously really important definitions, and I'm not going to spend a lot of time on those, really. You've just got to go away and you've got to learn those. You need to know every single one of those word for word. Now, there are some that come up more than often. Certainly, lattice dissociation comes up, enthalpy of formation tied into AS. They tend to come up. You don't see some of. I've not seen a definition of I don't think a bond dissociation enthalpy. I don't think that's come up before that I can remember. But still, you need to know it. Okay, so now that we've got those definitions sorted, and basically you've just got to learn those. There's no way to get around that, unfortunately. Going to have a look at actually applying some of that logic, some of that theory to a Born-Haber cycle, and to give this sort of a purpose, really, we're going to calculate the lattice formation of sodium chloride, and we're going to use these values. So, lattice formation. Before I start anything, and I'll run this out in a second, just think, well, what is this lattice formation? Well, lattice formation is the idea of obviously forming this lattice, this ionic lattice. So in this case, we're forming sodium chloride, a solid here. And the way we form that is we form it from our gaseous ions. So our Na plus and our Cl minus. Now we've got a variety of different values here. And really we've got to get to the point where we can calculate this. But by sort of the idea of Hess's law, we can go to, you know, A to B to C or whatever to actually get that value, and that will be the same as the entirety around here, and that's very, very important. And we can take that idea and we could use that, and that's how Born-Haber cycles work. So starting point, I always start here because I think it's the easiest place to start, and that is with the enthalpy of formation of whatever it is we're looking at. So for us right here, it's the enthalpy of formation of sodium chloride. So sodium chloride, obviously solid. Now, so we're forming this guy. What are we forming that from? Well, think about the reaction that occurs in terms of the enthalpy of formation of sodium chloride. It's Na, solid, plus Cl2, gas, obviously, to NaCl, solid. Now, that's not balanced. We could balance it using that and that, but that would be wrong by definition. So, we balance it using a half, which now makes it good. It now works perfectly. So, Na solid, half Cl2. It's a good starting point. Now the next bit you can do in a variety of orders. I'm going to stick in this order because I like it. I tend to do one element at a time. So this first one I'll deal with sodium. So let's atomize sodium. We can really do nothing else. We can't ionize sodium until we've atomized it. So that's got to be our first step, because the atomization by definition is of the ionization by definition is of gaseous atoms. Well, we can't ionize this because it's not gaseous, it's solid. So we atomize our sodium, and that's going to turn us into sodium gas. Still half Cl2, that's not been affected. Now we've got atoms, we can ionize. Now you could, at this point, you could say, well, I want to atomize my chlorine, and you'd be completely fine to do so, but I'm choosing not to at this point. So I've now made sodium ions, gaseous sodium ions, still my half Cl2, that's not changed. Now I'm done. I've got my Na+, which I want as part of my lattice formation. I need to get my chlorine sorted, so let's go over here. Let's turn my chlorine into just individual atoms. That's going to be a good next step. In fact, we don't need that there. So I've now produced chlorine atoms. Yeah, I don't need chlorine atoms. I need chloride ions. So get rid of this, give us a bit of room. What I'm going to do is I'm going to go around here, and I'm just using this ideas from what here. I'm not using any of the values just yet. So I've got chlorine gas. I need to make chlorine ions. So I go down this time because I have a negative value. You'll see for all the rest, a bit of a wonky line, I've gone up when there's been a positive value and down when there's been a negative value. What you've got to imagine, this is a scale of energy lower to energy upper. So we're increasing energy, we go up. When we're decreasing energy, we go down. So here, I've now become a chloride ion. So Na plus, gas, Cl minus, gas. Lovely job. And my final step now, because I'm now at this point I want to be at, this here, and this was my electron affinity of chlorine. This point here is my lattice formation, exactly as I want there. So now I have to think, well, how can I actually do this? Well, ideally, I would go from here to here. So that being NaCl over here. Just write that again so it's a bit clearer. But I can't, because I don't know that. What I need to do is I need to use Hess's law and the idea that I can go around or use an intermediate route to calculate the same enthalpy change, because I'm ending at the same place. I'm starting at the same place, I'm ending at the same place. So I go round here instead. And this line is obviously the bottom line here, so I go up and then I go down. Anytime you go against an arrow, exactly the same as in AS, you reverse the sign of what you've got. So I'm basically just going to put all these values together at the bottom here, and we'll see if we can get an answer. So our delta H of lattice formation is going to be equal to negative this value. Well, ordinarily my enthalpy of electron affinity would be minus 349. Well, I'm just going to have plus 349. Okay, so it's a minusing the minus. I'm reversing my sign. Okay, that's the easiest way, I think. Just reverse the sign, and I'm going to add on to that. Always stick at adding. It's easier. And I'm going down against this arrow now. Then this was my bad of me here. This was my atomization of chlorine, which was this one here, plus 122. So I'm going to add to that minus 122. I've just reversed the sign. I'm going to add to this the ionization energy of sodium. I'll just tick these off actually as we do them. Done that one. First, I know, so plus 496. Add to that minus 496. Add to that. What's my next one? Atomization. It's going to be plus 107. So add to that minus 107. Finally, this is going down. This is going with us. So we've basically taken this route here. We've gone up and then across like that. So basically against that one, against, but then with this one. That's a very, very important step, because that means we do not reverse the sign here. And so we just add on to this our normal minus 411. which is spot on. That's exactly what we want, so that's absolutely fine. And all you do then is you just add these numbers together. And when you add them together, you come out with a value of, or you should come out with a value of, minus 787 kilojoules per mole. And that there, with the minus sign, this is a very important point to make, that is the lattice dissociation enthalpy of sodium chloride, calculated as going using this thermochemical cycle. Now what you can also find is that they may have been sneaking. They may have said to you, use the Born-Haber cycle to calculate the lattice dissociation enthalpy. Well, the lattice dissociation enthalpy is this same thing but opposite, because the lattice dissociation enthalpy requires breaking this apart. Therefore it's a breaking bond process. Therefore it requires energy. So whilst the lattice formation enthalpy might be minus 787, the lattice dissociation is plus 787. So it would depend what you were asked to calculate here. This one we worked out the lattice dissociation, but we could easily convert that to lattice dissociation. Sorry, we found the lattice dissociation. We could easily no, we didn't. Start again. We found the lattice formation here. We could have easily converted that to lattice dissociation by switching that sign round. It all depends what you're being asked to calculate, so pay attention to the questions. Do one more example of this, just to give you an idea of how they work. This time we'll do the lattice we'll do the lattice dissociation this time, but of magnesium chloride. So let's have a go at this one. Values for this reaction are as follows. So what we've got here then are our various enthalpies, just similar to before, same idea, same values and all the rest, and we're looking to calculate a lattice dissociation for the magnesium chloride. So it works in exactly the same way. I would stick with this same way of doing it. It certainly works for me. I guess it perhaps wouldn't work for some people, but there we go. So, starting point. I would always start with the enthalpy of formation of our thing, so our magnesium chloride in this side. So enthalpy of formation, so we know we're going to form magnesium chloride. Nice solid there. Now how do we form magnesium chloride? Well, we obviously need magnesium and we need chlorine. So there we go. Nice and straightforward. Note this time I'm not halving this. It just sticks at CO2 because that's what we need. Mg plus CO2 gives us MgCO2, which does have an effect later on. That's why I've chosen to look at this one. And again, note that was find that there was a negative result, so I dropped down here. So I'm going to go up exactly as before. I'm going to do my enthalpy of atomization of my magnesium. So I'm going to make, and I'll just do this quite quickly. I'm going to then make Mg plus. I'm going to make Mg2 plus. Put our lines in, and then I'm going to obviously make my chlorine. So over here I've atomized it. I'm then going to ionize it first, and then going to ionize second to get to this point. And then what I'm going to do is I'll deal with my chlorine then. So this whole time chlorine's just been chilling out and hasn't been affected at all. It's just gas the whole time. CO2 gas, no problem. Over here, nothing happened to my magnesium. That needs to be as a gas. Don't forget your state symbol, very important. But this time I'm going to break this into my Cl. This time I need to put 2 down. I've got to do that because it's got to remain balanced, and that's the key thing here. And you'll see why in a second, because actually when it comes to sort of actually the formation, or that formation there works, but when it comes to the actual lattice formation, it's formed in this way. Excluding this state symbol very quickly, it's 2Cl minus, so I'm actually going to end up with 2Cl minus, and that's fine. So this is our atomization of the chlorine, it's fine. Going across, similarly to last time, rub this out first of all. So similarly to last time, drop down for our electron affinity. Note that we had to use 2, it shouldn't have mixed, skipped that point actually. I had 2 ionization energies. One to make my Mg1 plus, second to make my Mg2 plus. That's very, very key. They must be separate steps there. I suppose you could add them together as one, but I would do them as separate ones. Here I have my Mg2 plus gas, 2Cl minus now, gas. Be aware of that one in a second. And then finally, my change here, whoops, straight across, and I'll just write this again here so it's a bit clearer, but it's exactly the same. It's my MgCl2, that's solid there. And the process works exactly the same as last time. We want to start here, we want to finish here, but we can't, because we can't go down here to calculate our lattice. In this case, what would be a lattice formation, which we can convert to dissociation. So we go against this arrow, and then we go down here. So we go against this one, against, and with. So if we think about the values now, we want to put those in, and we want to actually work out a lattice dissociation. And we start with this one going against, but don't be tricked out by this. What we've got is we have a reaction. I'll do it in the middle here. We have Cl becoming Cl minus. That's our definition. That's the enthalpy change of that's electron affinity. That's the enthalpy change of that reaction. However, we've got 2. We're forming 2. So we're doing this. So actually, we've got 2 times that. So this first bit here, going against that arrow, we've got 2 times 3, 4, 9. I've got rid of my arrow there. Sorry, I've got rid of my negative sign. I've just gone for a positive there, but obviously I've hidden it. So 2 times that. We're then going to add that to this change here, which is our atomization of the chlorine. Again, same principle applies. I'm forming 2. Therefore, I've got to double this. So actually, rather than just 1, 2, 2, I have to do 2 lots of minus 1, 2, 2, because I'm going against the arrow. Very important. Now I can ignore having to double things up because I'm onto my nice sort of normal ground. Mg, the second ionization energy there. So we've done that one. We've done this one. Second ionization energy was 1451, reversed. First was 738, so reversed. And then on to atomization of magnesium, which is going to be 149. Obviously reversed again. And finally, I add to that my normal value, not reversing it, of my formation, which is 642. And when I add those together, I should find a value of 2526 kilojoules per mole. And that's the energy change for this portion here, which is the lattice formation. Now I need the lattice dissociation, which is therefore going to equals plus 2526 kilojoules per mole. It's a really important thing to do here. Start at a nice position. Don't start up here because it's just confusing. Start with this first enthalpy change of formation and then work your way up or down. Obviously you could go down and then up. I'd go in order though. I'd deal with one element at a time. You could start with chlorine, but I'd probably start with the metal one just through habit really, I guess. Start with the magnesium, whatever you've got. Go up, then deal with your element, chlorine, fluorine, whatever it be, and then overall work out your change. And actually, once you get your head around it, it's relatively simple, and there's nothing there that is actually too difficult. So, that's a couple of examples then, obviously, of the Born-Haber cycles themselves. So one of sodium chloride, one with magnesium chloride, giving you that difference and having to double up those values. I'm going to look at a bit of other stuff now, a bit of theory kind of stuff now. Oh, do bear in mind, actually, you could be asked to calculate any change here. You could be asked to calculate the enthalpy of formation, in which case you would obviously just go around, you would start here, and you would finish here, and you would just go around the other way to find the enthalpy for that formation. It all depends on the question that you're given, really. You've just got to sort of apply your knowledge to that question, but there's nothing to stop them doing that. Now, why was there a difference in lattice enthalpy for magnesium chloride versus sodium chloride? So sodium chloride was minus 787. This one was minus 2526. Why? Why was a difference? Well, lattice enthalpies are dictated, whether that be formation or dissociation, are dictated by the size of ion and the charge of the ion. So in this case here, I have an Mg2 plus ion, whereas in this case here I have an Na plus. So I have a greater charge here, and actually when you think about it, that makes sense. The greater the charge, the greater the number. The smaller the size, the greater the number. Basically, the stronger the attraction between ion A and ion B, the bigger these numbers are going to be. The more energy it's going to take to break the lattice apart and conversely, the more energy is going to be released when the lattice comes together. So either way, and that's dependent upon these points here, so do bear that in mind. So the size of the ion and the size of the charge, as you can see there, as from what I've calculated. Now, the other thing you can look at with Born-Haber cycles, and something that I think is possibly a little bit more of a difficult sort of application of them, is looking at the likelihood of various compounds forming. And you'll see various things in textbooks about this. And really what we can look is we can say, well, which of these compounds would be more likely to form? And it all depends on stability, really. And if we look at a compound, and we look at 3 compounds, let's look at 3 generic compounds. So compound 1, compound 2, and compound 3. Now we might find that for each, looking at the enthalpies of formation, the first one has an enthalpy of minus 100, minus 600 for this one, and plus 1500 for this one, which could be reasonably real. And I'll look at some values in a second that will of real ones, which will show you kind of what I mean. Now here, what we have is we find that when this is formed, this is obviously more exothermic than this. This one, to be formed, requires a lot of energy, which is probably very unlikely. So if you actually think about these terms here, what this actually means is that compound 2 is the most stable, and the reason is it's the most exothermic in its formation, which means ultimately it's the one that will form more readily. If we have a really endothermic formation, it's very difficult. You know, we've got to put in 1500 kilojoules of energy per mole in order to form it. Well, that's a lot. That's not going to happen. If actually we find that forming it releases a huge amount of energy, that's going to happen. That's a very stable way to be. That's very good. And also it means we've got to put in more energy to therefore break it apart. So that's a very stable way to be. So if we think about the charges of each of these compounds, let's imagine that the metal ion, the compound 1 is M+, and in this second one is M2+, and the third one is M3+. Take a step back and think about what the lattice enthalpy would be. So in this one here, the lattice formation enthalpy would get more negative. So it would get increasingly more negative as we went down. And that's because of these charges that are present. And what I'm doing here is I'm actually thinking, well, what if I were to have calculated this based on the rest of my Born-Haber cycle? So my lattice formation enthalpy, as my charge of the ion here increases, that also gets more negative. And the idea being that, remember, as I said, ion A and ion B, the stronger the attraction, obviously the more negative or the more positive the formation and dissociation are going to be respectively. And that's what we can see. M3+ ion, 3+ versus a 1-, well, we've got a much stronger attraction than the 2+, and therefore we're going to have a much greater lattice formation. And in that case, you might say, well, this is good then. This is brilliant. This is more stable because it's got a stronger lattice formation. But the problem we've got is that in this case here, and actually the example that I've actually drawn this from is actually the magnesium example, similar to the one above, where this one is actually magnesium chloride like that, this is magnesium chloride like that, and this is magnesium chloride like that. And actually in reality what we find is, excluding this sort of just made up example, still the delta H's here of formation. This one comes out at -94, this one comes out at -643, and this one comes out at +3949. And the same idea happens. We've got a charge of 1+, we've got a 2+, and we've got a 3+ for our metal ion. This one remains at -1 the entire time. That's fine. So as we go down here, as we get an increasing charge on our metal, we find the lattice dissociation enthalpy becomes more negative, and that's fine. Or the lattice formation enthalpy becomes more positive. Either of those is true, which might make you think, well, actually, that would give me a value of formation which would actually be more negative, and that's kind of true of this first two. We get a more negative value here, and if we go up to the Born-Haber cycle for this, and we imagine that in the first instance of the magnesium with a single plus, we wouldn't have this, in fact, wrong one there, we wouldn't have to worry about ionizing it there. We would just ionize it once to Mg+, overall meaning that we would have obviously a value of an enthalpy of formation which we would calculate, which came out at 94. As soon as we have to factor in then this second one here, we find now that this overall becomes, alongside now with our difference in lattice enthalpy and our ionization energy of the second ionization energy, we end up with a formation which is more negative, minus 642, which is fine, that's good, that's what we'd expect. The problem is when we hit our third one here, we hit our magnesium with 3 chlorines. Because our magnesium has 2 electrons in its outer shell, as we move down into the next shell, we find that we have a much greater third ionization energy, much greater. It's so much greater that it actually outweighs the change in lattice enthalpy, and therefore the formation becomes positive as a result. So what I'm talking about there is the idea of putting all these values in and making up new Born-Haber cycles for each one, which I'm not going to do because it ends up just becoming quite sort of long. And I don't really want to start putting in loads more diagrams and make it any more confusing than it is. But the idea is then that basically the balance between these various things ends up predicting, if you like, our which one will be more stable. So one more time, just to make sure I've made that sort of really clear. As we go down here, obviously we form a different charged ion. So the chlorine behaves exactly the same. So this diagram here will be the same in some respects. The chlorine will always remain the same. Obviously we'll have different values because we're going to produce less chlorine, etc., but we'll balance that up. However, the ions here would be different. In the first example, we would only ionize our magnesium once, which means we would eradicate completely our second ionization energy, and that would give us our value, which was minus 94, I think. In the second one, we do have to factor in our Mg2 plus the second ionization energy here, which changes the value but also changes the lattice dissociation enthalpy, and the overall change there means that because this difference here is greater than this, we end up with a formation that is more negative, and that's important. That's a very good thing. That means that it's more stable because it's more exothermic, the MgCl2, than the MgCl, actually exactly as we can see that. However, when we go to MgCl3, we have a third ionization energy here to contend with. Now that third ionization energy is so big it outweighs the change here, and because it outweighs this change, it actually means we end up with a formation which is positive. And so drawing this, the reason I haven't drawn this is because it can be a bit more difficult to draw, and you need a whole new load of values, which is not necessary, and it just overly confuse things. But if you look this up, look on ChemGuide or various things, and you'll see the actual values there. I don't want to spend too much time on that because it can just become needlessly confusing, and that's not really kind of what I aim for. So if you found that a bit confusing, listen again and see how it goes, and see if that makes any more sense. Okay, the final portion really to look at with all this is something called the perfect ionic model. And the way questions can be asked, and what they can look at, is this idea, as I say, of this perfect ionic model, and that brings itself down to a couple of sort of key points. The first being that when we look at values of lattice enthalpy, we can have theoretical values. So we can have theoretical values of lattice enthalpy, and we can have experimental values of lattice enthalpy. Now, what we find is that the Born-Haber cycle gives us these experimental values. So the value we calculate from our Born-Haber cycle is an experimental value, it's not a theoretical value. Now, we may see a couple of things occurring here. If we imagine a table looking something like this, so this table then shows me some lattice enthalpies, formation enthalpies, dissociation enthalpies for sodium bromide and silver bromide. Now we can see in this first example here, they're very similar. Now that means that actually we could say that obviously the experimental and the theoretical values are very similar, and then therefore we expect that we would be correct. Our theoretical value had obviously come out pretty well. Now what we need to focus on here, and this idea actually of the perfect ionic model really, and what that means is these theoretical values are based on a few sort of key points. First one's being that ions are perfect spheres. That's the first sort of key point that we look at in terms of the perfect ionic model. So What is the perfect ionic model? Well, it's in a model which assumes that ions are perfect spheres, and also that the bonds are 100% ionic. That's another one. And the final one is they are purely electrostatic attractions. There's no covalent interaction at all. And so if these two values are close, we can assume that we are close to this perfect ionic model, as we are with sodium bromide. That's absolutely fine. Silver bromide, however, these are different. The experimental value came out different from the theoretical value. And that means actually now that because that has come out differently, this one has some covalent interaction, or we could say covalent character. And the reason being that in this case here, the difference between the charges and the rest has caused for these perfect spheres and all the rest of it to not exist. And what we can find is that between our AG and our BR, we had some distortion of these electron clouds around here. Maybe the electron clouds were distorted, so it kind of went over here, or it was distorted over here in some way. But whatever happened, we had a distortion of the electron clouds, which moved away from this perfect ionic model. So some polarization occurred between the silver and the bromide ions, therefore bringing us away from this theoretical perfect ionic model toward an experimental covalent or more covalent model. And that's a very, very clear, that's a very, very sort of important point to make. Okay, the idea of this polarization causing this covalent character, and the differences basically between the experimental and the theoretical values being because of this polarization, therefore it moving away from this perfect ionic model where we have perfect spheres, 100% ionic bonding, and this pure electrostatic attractions. Instead, we're moving into the idea of having covalent interaction, covalent character. So that's the final part here to look at. Now, I hope that's been of some help. And there you go. That's the whole of Born-Haber cycles for the thermodynamics section of Unit 5.